All right, in this Le Chatelier's principal problem, we're going to look at several different stresses for this equilibrium, and we're going to try to explain what happens to the amount of ethane gas, the C2H6, in a vessel when we perform various stresses. So we notice here in this chemical reaction that we see a solid carbon reacting with gaseous hydrogen, and it produces gaseous ethane gas. The solid carbon mixed with gases is what tells me this is a heterogeneous equilibrium, and we have to be a little bit more careful because solids, of course, have constant concentrations along with liquids, and they're not included in the equilibrium expression for the reaction or in the expression for the reaction quotient. So we're going to be explaining the various stresses in terms of kinetics and Q. Let me quickly write the expression for Q. So Q is equal to the concentration of the ethane, C2H6, raised to the power of 1, divided by the concentration of hydrogen to the power of 3. And again, I've omitted the carbon because it was a solid. It's not part of the expression for Q. I notice that the delta H, the heat of reaction, also called the enthalpy change, is a positive quantity, positive 47.3 kilojoules per mole. The positive number tells me that this is an endothermic reaction. Okay, as written, the forward reaction is endothermic, which means the reverse reaction would be exothermic. Given that the forward reaction is endothermic, let me just quickly sketch our graph that shows for endothermic reactions how Kc changes with temperature. For endothermic reactions, when you raise the temperatures, the Kc's get larger like this. If it were an exothermic process, it would be a dropping curve. Okay? All right, we have all the tools we need. We can jump in and start answering the questions. Again, we're trying to figure out what happens to the mass of the ethane gas. So the first thing, if we add a small amount of extra carbon to the flask, what will happen to the amount of ethane in the equilibrium mixture? Well, you look at the expression for Q, let's talk about reaction quotient, and you see that carbon is not there. It's not part of the expression for Q, and adding the carbon doesn't change any of these concentrations. So because none of these concentrations change, and because carbon is not part of the expression for Q, then Q does not change. The reaction quotient is unaffected. Of course, the only thing that would change a Kc is if the temperature changed. So in this case, Kc doesn't change. Therefore, Q is still equal to Kc. The reaction starts off at equilibrium, so Q is still equal to Kc. Q is unaffected, Kc is unaffected. There's no shift in the equilibrium. Nothing will happen to the amount of ethane gas. If you prefer a kinetics explanation, you would note that carbon is a reactant in the forward reaction. However, it's a solid, and solids have constant concentrations. So because it's a constant concentration, adding more carbon will not affect the rate of the forward reaction. Of course, carbon is not a reactant in the reverse reaction, so the reverse rate is unaffected also. Since the forward and reverse rates are unaffected, there will be no shift in the equilibrium, and nothing happens to the amount of ethane gas. The second stress, add a catalyst. If you want to pause the video and check your own understanding, if you add a catalyst to the system at equilibrium, what will happen to the amount of ethane? So from a kinetics perspective, let's talk about that first this time. Adding the catalyst will speed up both the forward reaction rate and the reverse reaction rate. The catalyst lowers the activation energy for the reaction, and that will speed up both the forward and reverse reactions, and they speed up equally. That's a very important idea. They speed up equally. Because they speed up equally, the forward rate and the reverse rate start off equal, and they finish equal. Okay? They were equal before you added the catalyst because we were at equilibrium. When you add the catalyst, the forward and reverse rates each increase the same amount, and so they remain equal. Since they're still equal, there's no shift in the equilibrium. Nothing will happen to the amount of ethane in the container. From the perspective of reaction quotients, we would start by saying the temperature did not change, so Kc does not change. Q is unaffected by the addition of the catalyst because the catalyst does not change any of these concentrations. So Q is unaffected also. Since Q starts off equal to Kc, the reaction started at equilibrium, Q will still be equal to Kc when you add the catalyst because neither of those things will change, and therefore there's no shift in the equilibrium. All right, the third stress, let's withdraw hydrogen gas from the flask. Okay, so take out some hydrogen gas from this flask. Pause the video and see if you can predict the effect on the ethane. If you want to explain using kinetics, you would start by noting that hydrogen gas is a reactant in the forward reaction. When you withdraw the hydrogen, you're lowering the hydrogen's concentration. That means the forward reaction will decrease in rate. So the forward rate decreases. The reverse rate is unaffected because hydrogen is not a reactant in the reverse reaction. So the forward rate decreases while the reverse rate stays the same, which will result in the reverse rate being larger than the forward rate. Therefore, the reaction will shift in the reverse direction. Shifting in the reverse direction will use up some of the ethane gas, so the mass of ethane will decrease. Now, can we explain this using the reaction quotient? Looking at hydrogen, we notice that hydrogen is in the denominator of Q. So if you were to withdraw some hydrogen, you are lowering the concentration of hydrogen. And because it's in the denominator, dividing by a smaller number will make Q, the reaction quotient, get larger. Since the temperature didn't change, Kc does not change. So Q is larger than Kc. When Q is larger than Kc, a reverse reaction will occur. The reverse reaction will mean you end up with less ethane gas at the new equilibrium. The fourth stress involves heating up the flask. So we're going to heat it up, raise the temperature. Pause the video and see if you can explain what happens to the amount of ethane gas. So raising temperature. From a kinetics perspective, we know that when you raise the temperature, rates get faster. So raising the temperature will increase the forward rate and it will increase the reverse rate. However, they do not increase equally. The endothermic direction, in this case the forward reaction was endothermic, the endothermic direction will increase in rate more than the exothermic direction. So in this case, the forward reaction, which was endothermic, will increase in rate more than the reverse exothermic reaction. The forward rate will end up larger than the reverse rate, so the reaction shifts forwards to create more ethane. So the idea here is that when you change the temperature, you change the rates of both forward and reverse reactions. However, the reaction that was endothermic is the reaction which is affected to the greater extent. So if you had cooled this down instead of heating it up, both the forward and reverse rates would slow down, but the endothermic direction, the forward direction, would slow down more. So in that case, the reverse reaction would end up being faster, and you'd have a reverse shift. Okay? So in this case, heating it up increased the forward rate more than the reverse rate, so we ended up creating more ethane gas. Now what about Q and Kc? Well, changing temperature is the only thing that changes Kc. So we look at our graph. This was an endothermic reaction. In an endothermic reaction, when you raise the temperature, the Kc gets larger. So raising temperature caused Kc to increase. Q, the reaction quotient, is unaffected by a temperature change. None of the concentrations would be affected by changing the temperature, so Q does not change. So Kc is larger, but Q did not change, that means Q will end up less than Kc. When Q is less than Kc, the reaction shifts in the forward direction, and you'll end up with more ethane gas at equilibrium. The next stress, you want to decrease the volume of the flask. Some people would phrase that as increase the pressure in the system. So you want to decrease the flask volume. Pause the video and see if you can predict the effect on the amount of ethane. So decreasing the volume, the first thing I would say is that all of the gases in the container will increase in concentration. Okay, the concentration of hydrogen increases, the concentration of ethane also increases because the container's volume was reduced. Now, looking from a kinetics perspective, the rate of the forward reaction and the rate of the reverse reaction would increase because you've increased the concentrations of the reactants in both directions. However, in the forward reaction, the hydrogen, the only thing that would affect rate here is hydrogen, because the carbon, a solid, has constant concentration. So the hydrogen is third order, while in the reverse reaction, the ethane is first order. The coefficient there is a 1. So when you increase the concentrations of each equally, the effect on the forward rate will be greater. So both rates increase, forwards and backwards, but the forward rate increases more because the hydrogen's order is greater than the order of the ethane. So the forward rate being faster will shift the equilibrium forward and will end up making more of the ethane. The mass of ethane will increase. Now, from a Q and Kc perspective, changing the volume of the container, reducing it, does nothing to Kc. Only temperature will change Kc, so Kc is unaffected. However, Q will definitely be affected, or may be affected, let me put it that way. It depends on the orders in the numerator and denominator of the expression. In this situation, both of these concentrations, the ethane and hydrogen, will increase because the volume of the container decreased. But the denominator of Q, because it's third order, will increase to a greater extent than the numerator, which was only first order. Now be careful how you phrase that. Notice I said the concentration of ethane and the concentration of hydrogen will both increase, and they'll increase equally. But then, instead of talking about the hydrogen and ethane, I talk about the numerator and denominator of Q. The denominator of Q is third order, so increasing the concentration of hydrogen will increase the denominator more than increasing the concentration of ethane in the numerator, which was only first order. That means the denominator gets larger and Q will end up getting smaller. If Q is smaller than Kc, it'll lead to a forward reaction and you'll end up with more ethane gas at the new equilibrium. Finally, we add a catalyst to the system. What happens to the amount of ethane? You know what? I just realized we've already discussed that one, so we'll leave that last part out. Okay, that was a repetition. All right, so there's several different stresses explained verbally. I hope that helps in terms of understanding Le Chatelier. Be sure you're able to do this quickly in your head in a multiple choice question, but also clearly explain, like I've been doing verbally here, I hope, if it were a free response question.